variations on a theme. Today we have a look at sliding window approaches. So the theme is sliding windows, and we look at a couple of problems where we can use a variation of that theme in order to solve the problem. Problem number 1 is LeetCode question 1004, max consecutive ones number 3. Flagged as medium. Given an array A of zeros and ones, we may change up to k values from 0 to 1. Return the length of the longest contiguous subarray that contains only ones. So we get like two examples here with an input A, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, and k equals 2. And then the output would be 6 because we flipped 2 zeros into 1, and then we have like a longest consecutive sequence of 1, 2, 3, 4, 5, 6 ones. Then the next one is input A, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, and k equals 3. And then the output would be 10 because we flip those two middle zeros, like 1, 1, 0, 0 to 1, 1, 1, 1, and then immediately get like 7 out of them. And then flip the other 0, get 8, 9, and 10 all together. So the longest subarray then is 10. And we get like some notes on what's the maximum length of the array and what's the maximum length of k, just to be within the boundaries. Next one is the longest substring without repeating characters. So we already get a theme. The theme usually is like you find like the longest consecutive longest amount of distance between left and right in a longer sequence or in a string in a given bit set, etc. So here, longest substring without repeating characters, a problem that looks familiar. Given a string, find the length of longest substring without repeating characters. ABC, ABC, BB. Output 3. The answer is ABC with the length of 3. Input B, 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 output 1. The answer is B with the length of 1. Example 3, P, W, W, K, E, W, output 3. The answer is WKE with the length of 3. Note that the answer must be a substring, PWKE. And then the next one is 995, minimum number of k consecutive bit flips, flagged as hard. In an array A containing only zeros and ones, a k-bit flip consists of choosing a contiguous subarray of length k and simultaneously changing every 0 in the subarray to 1 and every 1 in the subarray to 0. Return the minimum number of k-bit flips required so that there is no 0 in the array. If it's not possible, return -1. For example, we have A equals 0, 1, 0 and k equals 1, so the subarray of length 1, and the output would be 2. We flip A0 and then flip A2, and then we only have ones in the array. Next one is A equals 1, 1, 0, and k flips, subarray is k equals 2, output is -1. No matter how we flip subarrays of size 2, we can't make the array become 1, 1, because whenever we flip a 0, we also have to flip one of the original ones. Then next one is input A equals 0, 0, 0, 1, 0, 1, 1, 0, k equals 3. Explanation, flip A, 1, A0, A1, A2, then we become 1, 1, 1, 1, 0, 1, 1, 0. Then next we flip A, 4, 5, 6 to become A, 1, 1, 1, 1, 0, 0, 0, and then we just flip the last 3 bits, A, 5, 6, and 7. And then again we have like some constraints on the length. Subarrays with k different integers 992 flagged as hard. Given an array A of positive integers, call a contiguous, not necessarily distinct subarray of A good if the numbers of different integers in that subarray is exactly k. For example, we have 1, 2, 3, 1, 2, 3 different integers, 1, 2, and 3. Return the number of good subarrays of A. Now we get like 2 examples. Input A equals 1, 2, 1, 2, 3. K equals 2. So the subarray is exactly 2. Output 7. Subarrays formed with exactly 2 different integers are 1, 2, 2, 1, 1, 2, 2, 3. Then of length 3, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Example 2. A equals 1, 2, 1, 3, 4, and K is 3, so 3 different integers. We have an output 3 because we can do 1, 2, 1, 3. That's 1, 2, 3 as the different integers. 2, 1, 3. That's 2, 1, 2, and 3 are the different integers there. And then 1, 3, 4 are the last 3 different integers that we can use. And also that comes with like some assumptions on the length of the array and on the numbers that are in the array and how many different integers we want to finally have in the subarray. And all of those problems can be tackled with a variation of the theme sliding window. Now let's have a look at a better definition of what we understand when we talk about a sliding window. And that definition has been nicely written up by Jordan Moore in 2019 in his blog, where he writes in great length about the different approaches using a sliding window. So I can highly recommend going completely through his website there. And he basically describes like 2 very basic problems where you can use sliding window. One, for example, would be to just like look at any pairs in a sequence of numbers and find the pair that has like the highest sum, I think, the highest sum of a given pair. And you can tackle that by just having a sliding window of fixed size with left and right being just like 1 position apart from each other, and then you just like move across with your window. And as you move your window across, you can leverage already the fact that 1 of the 2 numbers that are in the window is basically the same number from the last iteration. Like if you look at here 5, 2 and 2, 4, then the 2 is the same. So what you can basically do when you do your window approach is just like have your current sum, which in this case is 7, subtract the number that just falls out and add the number that comes in. So 7 minus 5 plus 4, minus 2 plus 6, minus 4 plus 3, minus 6 plus 1. And then just keep track, keep a maximum variable that just keeps track if you hit a new maximum. And if that's the case, then just like keep track of the maximum and maybe keep track of the positions as well. And then you're basically done with like 1 iteration over the array. That's with a fixed sliding window. But of course, there are more sophisticated cases where your sliding window basically has a varying length, varying size, depending on if you need to adjust your right end of the window or if you need to adjust your left end of the window. That can then lead to cases where the right part of the window gets bigger and bigger and bigger up until you hit a certain condition, and then from the left part you start decreasing again up until you hit like another condition, and so on and so forth up until your sliding window hits the other end of the sequence or of the string. They spend like a lot of time going through certain algorithmic descriptions here and some code formulations of the window approach. Later down, he's actually tackling one of the problems that we are looking at. Well, that was the longest substring, and with like a nice visual description on how to go through. So it's highly recommended to just like walk your way through this website look at the couple of problems and look how they were actually implemented. And here, as you can see, you can basically see step by step how that window of a varying size moves from the left end of the string all the way to the right end of the string. And as it's moving, it changes the size depending on the conditions that it's meeting while going through the array. And the conditions here is like, do we encounter a duplicate character or not? And if we encounter a duplicate character, what do we need to do to our window before we progress? And that's all to it to understand the sliding window approach. And now let's basically go back to the 4 problems that we saw and just have a look how sliding windows were used to tackle those problems. Maximum number of consecutive ones. What was that one again? Given an array A of zeros and ones, we may change up to k values from 0 to 1. Return the length of the longest contiguous array that contains only ones. And he's doing that by initializing a sliding window with basically 0 width, so the start and the end are at the exact same position in the left end of the sequence. And then we just keep track of what is our current maximum and how many counts, right? And our window will progress up until the right end of that window hits the end of the sequence. Then we are done with sliding our window through. Now we basically just check when are we encountering a 0. If we are encountering a 0, we immediately assume we can flip it. If our count hits the upper, like hits that condition that we say, okay, we have flipped more zeros than we are allowed to flip, that's our k, that's our if condition on the k. Then we need to adjust again. So here we adjust the left end of the window. So like, okay, the right end starts to slide over, and then once we hit that condition where we have flipped too many bits, then we basically need to start again by setting, by readjusting the counter. And that always happens if we have already encountered a 0. So that was like the last position where we have flipped. And then we basically go back and adjust the counter there. And here in the last 2 lines, basically we just keep track on if we had like a new maximum amount of ones that are currently flipped. And that's basically the number that we want to return at the end. So we slide a window, we adjust the width of the window depending on if we have met a condition where we have to re-evaluate our current situation. Longest substring without repeating characters, also with the sliding window approach and with like some really nice explanation coming with it as well. And he basically says like, okay, we start storing the character index mapping in an unordered map and then increase the length. Once we encounter a duplicate character, you know, like WW, which like violates the condition, then we need to readjust our sliding window, right? Optimal way is we store the old index of a duplicate character in a variable index, update the length of the current index, update the new index in the map, and most importantly, check if the character is found in the map. If the index is less than it should not be found. And where do we find the sliding window in here? He's starting to have this index condition. The index here is set to -1, and this index is basically updated. And then we have len is like the other end of the array. So then we basically go from int to len and update int and len is basically our varying window. So int and len basically are like left and right in this case, in this scenario. The problem of minimum number of k consecutive bit flips. which can also be solved with the sliding window solution. And nicely here we have a detailed drawing and a detailed explanation of how to actually tackle that. In that submission, we will add an additional value, the value of -1, to first set all the zeros with -1, then start our flipping, and then revert back to 1. So first is replace all the zeros in A with -1. Use a variable state. It can be either 1 or -1 to mark the window state. Use head and tail to represent the ends of the sliding window. Each element head will be updated as a head equals state, which is swept by the window, or like times equals state, which is swept by the window. Change the window state as state times equals -1 when an element a head times state equals -1 leaves the window, and then check the final window, which basically, if we do that with -1, we can flip between 1 and -1 interchangeably by just multiplying with -1. That gives like a nice flip all the time. And now let's just have a look here, basically where the sliding window theme can be found. Again, head and tail basically mark the range of the sliding window. Head, or the left side of the window, is initialized to the beginning of the array. And then tail is basically initialized with the range k consecutives -1. So it's like the range of the window as we are sliding it over. And then while the head has not reached the other side of the array, we'll keep working. And then we start moving our window and flipping it into, like, with state, like multiplying it with state. Once the tail has reached the other side, so once our right side of the window has reached the other end of the array, we flip our state. So if the state was -1, it is now 1. If the state is 1, it's -1. And we do the same thing, move the window again, and then multiply the array at that point with minus state, and then update the results, like how many times we would have to perform this bit flip operation. Right. And res is basically also the result that we want to return. And in the end, we're going to return res. So the final check that we only have to do is one more time to go from the beginning of the window to the end of the window. If at any point we were not able to see a flip into all the ones, we have to return -1, basically say it's not possible. Otherwise, we will update the result plus one more time if the state was able to be flipped or not. So then the last approach, the last problem, used a sliding window approach for solution, is subarrays with k different integers. And here it nicely also comes back with a nice like walkthrough. So he says, like, as already mentioned in the number of older threads, the main idea is that we can calculate the number of subarrays with at most k different numbers, and then subtract that number of subarrays with at most k-1 unique numbers. Then we still get the answer. The main question is, how do we calculate the number of subarrays with at most n characters? We use the sliding window to create a window with at most n characters. For each of those windows, we calculate the subarrays with at most n characters. So let's see how this works with the array 1, 2, 1, 2, 3. So the sliding window with at most 2 unique characters, and the subarrays, which were not counted, as follows. Sliding window is assigned the subarrays within sliding window. So 1 becomes 1. 1, 2 becomes 1, 2, and 2. 1, 2, 1 becomes 1, 2, 1, 2, 1, and 1. And 1, 2, 1, 2 becomes 1, 2, 1, 2, 2, 1, 2, 1, 2, 1, and 1. And then 2, 3 becomes 2, 3, and 3. So the total number of subarrays with the most 2 characters equals the number of subarrays in those brackets, which if you count them all together is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's have a look at the array 1, 2, 1, 2, 3. Sliding windows with at most 1 unique characters, and the subarrays which were not counted are as follows. We really just go through all those digits one by one. 1 becomes 1, 2 becomes 2, 1 becomes 1, 2 becomes 2, 3 becomes 3. So the total number of subarrays with at most 1 character is the number of subarrays in those brackets, which is 1, 2, 3, 4, 5. So the final answer is all those 2 combinations, all of them, minus the 1 combinations, which is 7. Okay, that basically answers the question if we have n characters, what's the thing with, or like if we have k different numbers, how do we subtract k minus 1 characters? And that basically that theme finds here in the sliding window approach as well, where he's basically doing like 2 while loops, an outer while loop and an inner while loop. And then the outer while loop just waits up until the sliding window's right side has reached the end of the array. And the beginning of the sliding window is initialized as 0 size, and then it grows and slides over. Right? And so the whole updating operation basically works inside the inner while loop, where we can see at the end, while the sliding window size still equals n plus 1, we will update the left window. And then in the outer while loop, or like the left part of the sliding window, and then in the outer while loop, we update the right part, and then continuously grow our sliding window and go through them. And that's basically all to it. When you apply a sliding window approach, you always have like your left side and the right side of the window, and then either you move it through your array with fixed size, or you continuously grow and shrink while keeping track of your information that you want to gain from it, and while also applying logic as to when to update the right side or the left side of your sliding window. Then your termination criterion is left side or right side hits the end of the array. And that's basically all to it when you want to utilize a sliding window approach.